All right, so along came Tycho Brahe. I feel so bad for this guy. This guy, he wanted to prove Galileo wrong. That was his sole mission in life. Let's prove Galileo wrong beyond a shadow of a doubt. So he actually had a cousin that was a lord of something and so very rich. And he convinced his cousin to build him a tower, and he projected the telescope um, to build him this tower so that he can just basically sit there and look at the stars and prove Galileo wrong. Now, this guy Kepler, and that's a picture of Kepler up there, he didn't have very good eyesight, but he loved astronomy. He loved the way the stars would move, but he can't sit there and stare at the stars because at least not good enough to study it. He didn't have good eyesight. So he's actually the father of theoretical science, which is hence Sheldon. And so what he did is he went to Brahe and he's like, hey, I heard about what you're doing and I love it. Are you doing any analysis on it? And Brahe's like, well, So he's like, hey, can I do the analysis? So he paired up with Brahe. And then shortly after that, Brahe died and left Kepler with 25 years of data and diagrams, basically. Right. So think about you paired up with somebody because you don't have very good eyesight, and they died and gave you 29 years worth of Excel sheets. Where in the world are you going to start? The patience this guy must have had. And Kepler is like, I need a simpler theory, right? Because the theory we had now was still either one you want to go with, the sun or the earth. They both had epicycles. They both had lots of circles. They were both very complicated. He wanted a simpler way to do this. So he used Brahe's data and found 3 laws of planetary motion. So his first law. Planets' orbits are shaped like ellipses with the sun at one focus. Poor Brahe. His life work was dedicated to proving Galileo wrong, and Kepler comes along, takes his data, and proves Galileo correct. Ouch, that guy must have been turning in his grave. And then not only did he say, no, Galileo's right, it's the sun we all go around, not us, he said, the sun is at one focus. So not even the center, and we'll talk about an ellipse in the next slide too, but not even the center, one focus. And the orbits are not circular. They're elliptical. So everything we believe has just went out the window. First law. Okay, so what is an ellipse? Okay, it's basically a squished circle. Okay, you have a center in the middle, and you have 2 foci. And so he's saying the sun is at one focus, not even the center. Okay. You have a major axis, you have a minor axis. The major axis is the longer one, the minor axis is the shorter one. Right. That's not a big deal. But 2 other words you should know, perihelion and aphelion. Perihelion means you're closest to the sun. Oddly enough, for Earth, this happens in, yeah, you thought I was going to say July. Nope, January. And aphelion, furthest from the sun, that's July. So Kepler's second law. A line connecting the sun to any planet sweeps out equal areas of the ellipse in equal amounts of time. All right. So what? Something about lines and areas and time and yeah, I know. Here's it written out for you. But basically what it's saying is if you look at the diagram, you've got area A and area C. Okay. Area A, it's kind of long and skinny, but if you look at that little red line, the actual orbit of the planet is just a short little part, right? Area C, the orbit of the planet is that red line, so it's a pretty large red line. What his second law of motion is essentially saying is that the time it takes for a planet to go around the red line that's covering all of area C and the red line that's covering all of area A, so the big red line and the short red line, that's the same amount of time. So the closer you get to the sun, the faster you're going to go. The further away you are from the sun, the slower you're going to move. That's his second law, explained and summed up, hopefully. All right, so his third law is kind of a little bit more complicated. The square of a planet's orbital period is proportional to the cube of its semi-major axis. So basically what he's saying, what your takeaway here, is that your period, the time it takes for the planet to go a complete orbit, is somehow related to the distance of the orbit. That's basically what you need to know. Okay, so here's a little bit of the definitions. Orbital period, time it takes for a planet to orbit the sun. Semi-major axis is always measured in an astronomical unit, otherwise known as an AU. Astronomical unit, AU. Right. Now, 1 AU is the average distance from the Earth to the sun. Okay. And if you look at the ellipses, you're like, well, wait, one side is really short and one side is really long. Well, that's kind of exaggerated for you. The orbits are almost circular. Not quite, but almost. And so the average is not that bad. So 1 AU is basically the distance from us to the sun. And then his third law is right there, square of the period is it's equal or proportional to the cube of the AU. So written out mathematically. But again, basically, the time it takes for it to go around the sun is somehow related to how far away it is from the sun. Okay, I put this in here mainly so you can see the chart. There's something really interesting about the chart. If you look at the last column, which is Kepler's third law, they're all approximately, I mean, you can round off to 1. Right? I mean, 1.002, 0.998, right? You're all around 1 there. Which to me is just amazing that Kepler found this. Right? What was Kepler doing? He was going through 29 years of essentially hand-drawn Excel sheets. And somehow he fiddled with it enough that he found out this ratio works. The patience that man must have had is just remarkable. On the next slide, there's going to be kind of a nerdy looking guy, to be quite honest, going over the 3 laws of Kepler. I like to include it just because it's another person explaining the 3 laws. So if you didn't quite get it with me, maybe this guy will help you out a little bit.
How do planets orbit, and are there any specific ways that we can use to describe what's happening when they orbit? We actually have 3 basic laws called Kepler's laws of planetary motion that help us to describe what's happening when planets orbit the sun. Johannes Kepler was the astronomer who developed these planetary laws, and he used the data on the planets collected by a fellow astronomer named Tycho Brahe to develop these three planetary laws. Tycho Brahe was a flamboyant, naked-eye astronomer who had a gold nose to replace his, which he had lost in a rapier duel. Now, Kepler's three laws of planetary motion are the law of orbits, the law of areas, and the law of periods. The law of orbits states that all planets move in elliptical orbits with the sun at one focus. Now, this allows there to be a lot of different sizes of orbits, but all planets orbit in ellipses. Now let's look at some key pieces of an ellipse. There is also the major axis, which passes through the center of the ellipse and is the longest diameter of the ellipse. It's also called the transverse diameter. The minor axis passes through the center of the ellipse as well and is the shortest diameter. There is also the semi-major axis, which goes from the center of the ellipse to the longest edge, and the semi-minor axis, which goes from the center of the ellipse to the shortest side. There are also two foci, and remember that the sun is always at one focus. Now, when we're talking about orbits and ellipses, there are two other terms that can be helpful. They are the perihelion and the aphelion. The perihelion is when the planet is the closest it ever gets to the sun, and the aphelion is the furthest the planet gets from the sun. Now remember that Kepler's law of orbit states that the sun is always at one focus of the elliptical orbit. Kepler's next law is the law of areas. Kepler's law of areas says that a line connecting the sun and the planet would sweep out equal areas in an equal amount of time. Now let's look at this definition a little more closely. If we have a planet that's close to the sun, it's going to be moving faster and it's going to sweep out a particular area. What Kepler's law of orbit says that that same planet, when it's farther away from the sun, will be moving slowly and will still sweep out the same amount of area in the same amount of time. Basically what this means is that when planets are closer to the sun, they're moving faster, and when planets are further from the sun, they are moving slower. Kepler's third law, or the law of periods, says that the square of the planet period, or the time it takes for the planet to orbit the sun, is proportional to the cube of the semi-major axis. What this basically means is that the further away a planet is from the sun, the longer it takes to orbit, and the closer a planet is to the sun, the quicker it orbits. This is often written as t squared equals a cubed. Now we can look at this graph and see that planets that are further from the sun, like Neptune, take longer to orbit than planets which are closer to the sun, like Mercury. Now we can use Kepler's three laws of planetary motion to describe the orbits of lots of other objects, such as comets, moons, or even binary stars, where we have one star orbiting a second star. And these three laws, the law of orbits, the law of areas, and the law of periods, all apply to these situations.